Hey, welcome back. We got another 90-something degree day here in Texas, but at least there's a bunch of cloud cover, so I'm not burning up like I was last time I was on this outcrop. I'm Dr. Anton Robleski. I'm a sedimentologist, stratigrapher, and paleontologist. You know, a lot of times you're driving down the road and you're seeing some interesting rocks, you're kind of curious about them, or maybe you've been on a tour with a geologist or a paleontologist, and they're pointing out all these cool features and saying, oh, that was a river channel, oh, that was a beach, that was a barrier island. You might even have one of those roadside geology books that are really popular nowadays, and you're thumbing through it as you cruise along, and you look and say, oh, you know, this is a carbonate platform, or that's an intrusive pluton, and you think, how the heck do these people know this? What is it they're seeing that I'm not seeing? What I want to do today, though, is walk you through and show you that it's not really magic. We're using basic principles, first principles, things like grain size, color, texture, basic concepts of physics, some chemistry, some biology. Nothing magical, nothing out of the ordinary. Now, to interpret any outcrop, or even any core or rock sample, there are 8 basic variables you're looking at. These are the observations, the quantifiable, repeatable observations that are going to facilitate your interpretation of the outcrop. You're going to look at the rock type. Is it igneous, metamorphic, or sedimentary? Now, I'm not going to get into the differences of those in this video. There's plenty of other videos out there on YouTube. Lots and lots of people have done them. You'll find them with a couple of keystrokes. I'll tell you right off the bat, this one here is sedimentary, so I'm saving you that hassle. We also need to decide whether it's a clastic sedimentary rock, a chemical sedimentary rock, or a biogenic one. Now, this one's clastic because it's made out of smaller rock fragments and chunks of other debris, not skeletal remains of invertebrates or chemical precipitates. The next thing you're going to look at is major surfaces in the rock. So let's take a look at this outcrop and see if we see any major surfaces. I always tell my students and any professionals and industry people that I have out here in the field, before you go running up to a rock, you know, a lot of people want to run up and start checking it out and see if there's any cool stuff in it, and that's all well and good. The first thing you want to do, though, is stand back. So we're going to stand back and just kind of take a look and see what we see before we get up to it, because you can actually see a lot just by standing back. So with this outcrop in front of us, the first thing I always tell anybody that's coming out in the field with me on a trip is notice if there's any big changes in slope, in color, in dip, anything at all that jumps out at you. So I would say first thing anybody might notice in this outcrop is that that lower part is fairly vertical and it's a light color. Then about halfway up, there's sort of a ridge, which looks like from here even, you can see some coarser grain material in it. And then the upper part of the outcrop is darker, it's kind of a reddish brown, and it seems a little bit more recessed. Okay, so we're getting somewhere. Right off the bat, I would say we have 2 chunks of this outcrop. We have 2 sections. We can call them Unit 1, and we can call them Unit 2. Looking at Unit 2, I would actually even say you could probably spot another surface going through there that separates the lighter part of Unit 2 from the redder color that we might call Unit 3. Now, mind you, I'm standing probably about 20, 30 meters away from this outcrop, so about 70 feet away. We might change our mind when we get close, but that's okay. We are just getting the feel of this thing before we get up close to confirm. Remember, science is iterative. You're not just coming out with an answer and saying that is the answer. With science, you're trying to make the best observation and interpretation you can, then you gather more observations, and you go back and revisit and change your interpretation if that's what's required. So we've got our 3 rough lithological units broken out in this outcrop: bottom, middle, and top. Step 3 is the bedding. And by bedding, that just means we're going to identify any through-going sedimentary surfaces. If it was an igneous rock, it would not be a sedimentary surface. It would obviously be a different kind of surface, but it would be a surface indicating an individual bed. So we're going to go ahead and start tracing those beds. In the lower part, it's really hard to see much in the way of bedding. It's mostly kind of massive looking. You might see some horizontal beds going through. Let's draw our eye up though and take a look at that coarser grain material. If we zoom in a little bit, you can actually see it's gravel. It's cobbles, it's gravel, it's chunks of rock, and we'll go over it a little bit and examine the size of it. Again, we're just doing this from afar, but it looks like those gravel beds actually are slightly dipping down towards us. And if we trace them out on a photograph, which with modern software, you can do this directly into your phone or your iPad. You can do it on photographs. There's all sorts of ways of doing this. But if we just go ahead and draw in some lines on that first bunch of bedding in Unit 2, we can see what they look like. Okay, that's interesting. So they do seem to be dipping down towards us. Now, that's not just an optical illusion caused by the angle that we're on the outcrop. They really are trackable from top to bottom. In the upper unit, it looks like there's some gravel beds as well. And they seem to be at a slightly different angle. In fact, they seem to be going the opposite direction. And we'll get to that in a second. So we do have some down-dipping beds in that Unit 2. Interestingly, about halfway up Unit 2, there seems to be yet another surface. And that through-going surface seems to have beds that are dipping down onto it, and it seems to be truncating beds down below. We might go nuts. If you're feeling bold, we can make Unit 2 into Unit 2A and Unit 2B. Let's go ahead and do that. So now that we've identified Units 2A and 2B, we can go about taking a look at Unit 3, and sure enough, yes indeed, those beds are dipping in the opposite direction. They're dipping towards, in this case, it's towards the north, whereas the beds in Unit 2 are dipping to the south. So we have gravelly beds dipping north and dipping south, depending on which unit you're in. So now that we know the rock type, it's sedimentary, and now that we know that there are major surfaces going through it and separating it into at least 3 units, and Unit 2 has subunits A and B, we can go about identifying our geobodies. A geobody is essentially any self-contained unit that you can identify on the basis of lithology, bedding, grain size, and so on. This outcrop is pretty limited in lateral extent, so the lower part really doesn't go any further than the bushes, and it disappears into the trees down on the other end. So we're kind of lost there. But the upper part, Unit 2 and Unit 3, do seem to have some shape to them. So Unit 2 actually does have a pinching out shape. So the lower one sort of pinches out, then there's that truncating surface that comes through, and there's an upper one that has discrete downward dipping to it. So these geobodies, we would classify, they're not sheets, they're sort of lozenge shaped, or maybe lensoidal. And there's different shapes of geobodies you can apply based on your criteria. You know, people use descriptive shapes. They'll say things like lozenge or lentil, or sheet or ribbon. So in this case, we'll call them, maybe they sort of look wedge-like or lozenge shaped. All right, next up is grain size. This is true whether you're looking at igneous, metamorphic, or sedimentary rocks. The grain size, in other words, the size of the individual grains of minerals in the case of igneous rocks, or clast in the case of clastic rocks, could even be carbonate chunks, could be shells and carbonates. Those are the kinds of things that we're looking for, because that can give us a lot of information. Information about the energy that was present during the time of accumulation. Again, this is a clastic sedimentary rock, and it makes sense. Coarser grains require higher energy than finer grains. So by going through and looking at the grain size, we can get a pretty good feel for what kind of energy was happening when this stuff was accumulating. That in turn can really narrow down the depositional environments that were responsible. So it's helpful in identifying analogs, and we'll get to that in a second. So before I run across the street and look at that outcrop, take a look at this right behind me. The same outcrop is forming a cliff right here. It's pretty convenient. So I can take a look at the same exact layers on this side of the street as there are on that side. Now that's kind of a hard scramble. It's a little bit steep and it's a little bit tricky to scuttle up. So we can take a look at it right here. And that's what we're going to do. Incidentally, you can see where they've reinforced it with cement to prevent it from eroding, because this stuff erodes very quickly and readily. All right, here's that lower surface. So we can take a step back to step 2 in identifying rocks. Remember I was talking about stratal surfaces. Here's one of those stratal surfaces. And it's separating this lower section of kind of multicolored gray and red and ochre colored rock from, holy cow, this super coarse grain material. How coarse-grained is it? Well, these rocks are about the size of avocados, grapefruits, you know, peaches, all kinds of fruit-sized rocks. But they are very coarse-grained. This is gravel. In fact, these are cobbles. This takes a lot of energy to move around. So we've got a system that's depositing a very high energy deposit here, and it's very sharply truncating a system that's fine-grained. How do I know it's fine-grained? Well, you can see the grain sizes. Look at this stuff. It's very crumbly. You can feel it's like a silty clay, and if you want, you can even taste it. You know, in some of my other videos, I showed you guys the most sure way of identifying grain size in a clastic deposit. In some cases, it was not really obvious, like this cobble conglomerate above me. The surest way is to chew on it. And you can tell with your teeth, if it's really creamy, it's probably a clay stone. If it's a little bit gritty, it's probably a silt. And if it's got grains, you're probably dealing with a sand. So let's find out what this is. Let's get a good chunk. Oh, here we go. That's a good chunk. Look at this nice multicolored stuff. I'm going to bet it's a clay with some silt. This kind of feels like that. Yeah. That is a silt with only a little bit of clay. So it's actually a siltstone. But take a look at all the reddish material. There's a lot of oxidation in there. And oxidation like that is pretty typical of something that's been subaerially exposed. We'll get to that later when we're talking about interpreting depositional environments. But right now, just kind of keep a mental checklist as we're going through. So we've got an oxidized siltstone with a very sharp surface and a conglomeratic body on top. Now we're going to turn around and look back the opposite side of the road and get a better view of those dipping beds. Okay, so here's a better view of the dipping beds in Unit 2, and you can really see that it was not an optical illusion. They really are dipping from upper left to lower right, and they are all gravel lined. So that's telling us something really important about Unit 2. Remember, Unit 2 has that lower scour surface that I'm sitting on right now, and there's the silt underneath, the very coarse-grained conglomeratic gravel on top of the sharp surface, and then there's those dipping beds. That all goes towards helping us paint a picture of what these rocks represent. Okay, number 6, we're going to look at what's called sedimentary structures. In other words, that's little laminations, that's little small-scale features within the bedding. So those beds are the layers of rock, but within those beds we might see little bitty lineations, things like ripple lamination, things like trough cross bedding, things like hummocky and swaley bedding. And again, there's plenty of YouTube videos out there. I've even got a couple on these types of structures, so I'm not going to get into them right now. The important thing to understand is that sedimentary structures form in response to the physics of the processes that were depositing sedimentary rocks. High energy yields very planar lamination. Low energy can lead to undulatory beds. We can get things like ripples and trough cross beds. Now those are still pretty high energy, but they're not as high as sheet laminae, where the sediment and the water is moving so fast, nothing can form in terms of beds. So let's take a look and see if there's any bedding features, any sedimentary structures in this rock that can help us identify what Unit 2, 2A, and even 3 were formed in. Okay, I'm down here in Unit 1, and you can see there's a lot of horizontal lamination behind me. So you see these kind of rusty beds and the gray and the rust and the gray. Not a lot in terms of exciting bedding going on here. It's pretty regular, but take a look at that surface that separates Unit 2 above from Unit 1 here. It's going along horizontal, but look at this. Oh my goodness, it gouges out. It scours down in, shoots back up, and then cuts down. And we can actually see horizontal laminae, horizontal bedding in Unit 1 is truncated. It's cut, it's incised by Unit 2. Okay, so this is getting us somewhere. So the sedimentary structures in Unit 1 are being cut down into, they're being scoured out, in this case, really spectacularly, by the gravelly coarse-grained material of Unit 2, which then has those big gravelly laminae dipping down. Now, unfortunately, there's a lot of wash on Unit 2. You can see there's a lot of mud just kind of washing over the entire surface of the outcrop. So we really need a clean face to find sedimentary structures. This is not where we're going to do it. So maybe let's run back across the road and see what we can see over there. So unit 2 here has that basal contact with unit 1. It's that really sharp scour. And you can see back over there, it's actually cutting down at an angle and cutting across. But in terms of sedimentary structures, this is pretty massive. There doesn't seem to be much in the way of ripples. It's just too coarse grained. And again, unfortunately, where it's finer grained, you don't really see any sedimentary structures other than some little gravel stringers in amongst the fine grained material. There is a clue in the gravel though. Take a look at this. Oh yeah. See how the longer axis of the clast is dipping to the north? And lo and behold, so is that one. And so is that one. And so is that one. A lot of these gravel clasts, and a clast is just any sort of particle that's moved by the flow. Take a look at that. A lot of them are dipping to the north. That's imbrication. And if you spend any time wading around the modern streams with a lot of gravel, you recognize that, because imbrication indicates flow direction. And in this case, it's indicating the upstream direction is that way. So imbrication, these clasts are actually dipping upstream. It seems counterintuitive. A lot of people think it's the other way around, but go out. I encourage you to walk around the stream and see which way the long clasts are dipping. They're actually dipping upstream. So the flow is this direction to the south. Okay, a little bit of information. So we've got good observations. That is that a lot of the long clasts are kind of dipping to the north. And we've made an interpretation, which is that it's imbrication. All right, and interpretation is where people like to argue. So if you want to argue with me that that's not imbrication, you're more than welcome. Come out, gather a bunch of statistical data, and I'm happy to chat with you. So let's take a look at Unit 3 and see if there's any information on grain size, sedimentary structures, and so on. It's a bit of a hike up that hill, but we're in luck because right across the road, here it is. So we can actually take a look at it right up here. Let's see what we see in it. Interestingly enough, the top of Unit 2 is that silty material, just like we saw back there at the base. So we've got silt at the top of Unit 1, and now we've got silt with that rusty mottled appearance. I slipped. At the top of Unit 2, 2B. And then we've got the coarse grain material of Unit 3 again. Okay, so again, we're not seeing sedimentary structures in Unit 3. There's a lot of wash, but it's very coarse grained. But we are seeing some interesting patterns and textures in the top of Unit 2B. That mottled texture is a result of oxidation, and it actually feeds directly into our 7th observation. The 7th variable you need to take into account when you're trying to interpret an outcrop is trace fossils. They're unbelievably helpful. They're unbelievably overlooked, even by most professional sedimentologists, because they're not really certain how to interpret them, how to observe them, or what they're seeing. Let's take a closer look at the top of Unit 2, and I'll explain what I'm talking about. So these are the rocks at the top of Unit 2, and you can see Unit 3 sits directly on top of them on a really sharp surface lined with conglomeratic cobbles, gravel, larger clasts like that. There's none of that at the top of Unit 2. Instead, we've got vertical lineations chock full of reddish streaks in amongst a paler, lighter colored, almost a mint green color. Now that's reflecting chemistry. That's geochemistry in action, but it's also a biological process in action. I've talked about this in a couple of other videos, and if you haven't seen them, that's okay, because I'm about to talk about it again. Generally in sedimentary rocks, this kind of mint green, kind of grayish green color is a product of a reducing environment. In other words, there wasn't much oxygen. The minerals that were deposited in here did not get a chance to rust in place, which is what oxidation really is. So that usually equates to high water table, standing water, a pond, river bottom, or a wet floodplain. The reddish material, in particular vertical red streaks like this, indicate there was oxygen introduced into the background matrix of the greenish reducing substrate. And the most common way of doing that in sedimentary rocks is through burrowing and roots. Roots and burrows, in particular in a floodplain, can completely churn the upper few feet to several meters of substrate. And we can see that by looking right across the way. Just take a look at all the roots. You can even see them coming down into the deposits, and just picture all of those roots introducing oxygen into those deposits. We've got grasses, we've got bushes, we've got trees, each one of them effectively helping to rust the sediment a little bit more. Those tree roots across the way in particular are really helpful for picturing what's going on. Each one of those little root tendrils is introducing oxygen. So we've got, just from one tree alone, dozens, even hundreds of pathways for oxygen to infiltrate the sediment. So in terms of interpreting our sedimentary environment, it's really helpful to notice that fine-grained material like this, when it's heavily what we call mottled, and mottling just refers to that kind of mottled color, even the texture of that kind of red and the green or the gray and the orange, that's very typical of a floodplain deposit, something that's been rooted subaerially. Again, this all goes towards building the picture. So we've got a coarse-grained deposit at the bottom, it's finer at the top, each of those geobodies we talked about, coarse at the bottom, fine at the top, and evidence of rooting at the top before the next coarse-grained one comes in and goes up to being fine again. Now we're getting somewhere. We're really close to the end now. All right, we're almost at the end of gathering all the information we need to interpret this outcrop. That leaves just one more task before we can identify what these rocks are. We need to find an analog. Now here's where the fun starts, because analogs can be anything. It could be modern sedimentary environments, it could be rock deposits that you've looked at around the world or other people have published. What you're looking for is an environment that has the same characteristics as this. So we're looking for something that's got a scoured base with coarse-grained material at the bottom, big down-dipping lineations of conglomerate with cobbles and gravel, and the upper part of that body needs to have a rooted, subaerially exposed, really bioturbated and mottled fine-grained deposit before the next coarse-grained material comes through. I've got one in mind, and that's going to be our next stop on this trip. So we're going to leave this outcrop and go take a look at what I think is a pretty good analog for it. Plus, it gives us some time in the vehicle. We can kind of cool off with the AC, because even with clouds, it's pretty hot today. A short drive later, and here we are. We're at our destination analog. It's the modern-day Colorado River, and we're going to take a look around on this bar. Our depositional analog for units 2 and 3 on the outcrop needed to be sedimentary clastic bodies that are coarse-grained with highly angled dipping accretion surfaces or depositional surfaces. It needs to be something that's got a scour at the base that cuts into older, finer grained deposits, and it needs to be something that gets finer grained as you go up section and includes roots and insect burrows and a lot of mottling in fine-grained soils at the top. What I'm describing is this point bar here on the Colorado River in Texas. Check out the upper surface of the point bar. It's very coarse-grained, and it's actually dipping down to the river, and it continues to dip down under the water. Point bars like this have high angles of dip, just like we saw on the accretion surfaces back there. Not only that, but look at the grain size. This is coarse-grained stuff. Not quite as coarse as what we saw in the last outcrop, but it's still pretty coarse. Now, there's a lot of clamshells here, little bivalves, mussels, and we did not see them on the outcrop. That's because they dissolved. Groundwater, which comes from rainwater, is naturally acidic. So all these little shells that we're seeing tend to get dissolved and form carbonate cement. And I should have brought some hydrochloric acid onto the outcrop, because if I dropped it, it would have fizzed. These things react with hydrochloric acid. After the shell gets dissolved and percolates through, it creates a carbonate cement. So this coarse-grained point bar with the high-angle accretion sets dipping down into the channel, I think is a really good analog for what we were seeing back there at the outcrop. A point bar forms as a river flows and deposits sediment. So the river incisors and creates that basal scour, and then the bar results from the accretion of the sand and gravel laterally downstream and even upstream. These animations have been done by Zoltan Sylvester at the University of Texas, Austin, and they show really nicely how streams change over time in a really short time frame. And geomorphologists have been mapping this for over a century. Here's a great example from the Mississippi River Valley showing the network of channel belts that have evolved over the last tens of thousands of years. So with these analogs in mind, we can take a look at our outcrop and interpret it as 3 different bars that have incised one on top of the other over time as the channel belt migrates. So this is reasonably convincing, but what about other sedimentary environments? Could that outcrop have been a beach? Well, beaches have very, very fine-grained sand to fine-grained sand. This tends to be quartz-rich. Not a lot of gravel, not a lot of conglomerate. Beaches also tend to have very unique sedimentary successions that include sedimentary structures like hummocks and swales down below, low-angle planar beds at the top. You would see crab burrows and not a lot of rooting. That's not what we saw at all. What about a tidal inlet? Tidal inlets can be pretty coarse-grained, but again, you would see some evidence of more regular cyclicity. You wouldn't have necessarily as big a grain size as we saw. We saw some big cantaloupe-sized grains. Fluvial channels have the combination of scoured bottom, very coarse-grained accretionary sets, and importantly, take a look at that. The tops of the bars have a nice veneer of fine-grained silt and mud from when it floods. That silt and mud has a lot of rooted vegetation and insect burrows, and it creates the kind of modeling we saw. So we have coarse-grained material topped off with mottled, fine-grained, rooted horizons, just like what we saw in the outcrop. So that's it. That's how I go about working through an outcrop. That's how most sedimentary geologists go about working through an outcrop. I did one last year at Flaming Gorge Reservoir. It was a shallow marine sand. This one we just looked at was a fluvial channel system with a couple of bars building into it. Let me know if you like this one. Go ahead and comment down below. I'm happy to do more of these. I think there's a lot of really cool outcrops out there that we could work our way through systematically, and I can break them down like this. If you think it's something you'd like to see, let me know. And as always, thanks for watching. I will see you on the outcrop.